Notion looks like a document editor, but it is not a document editor. Everything that you see on the screen, every paragraph, every heading, every checkbox, every embedded database that you see, everything is the same kind of object. They call this object a block, and the entire app is built around just one decision. What if everything was a block? This decision is why Notion feels different from every other doc editor which you have used. This is the reason why you can drag a paragraph into a toggle, turn a heading into a subpage, embed a database inside any block. It is also why this is an interesting system design problem, and we are covering it today. Today I'll do two things. First, I'll walk you through how Notion's data model actually works. Then I'll build the working clone with the same architecture which is deployed also. So now let's start with the data model, which is the block model. Here's how a Notion page looks like. A heading, a paragraph, a toggle with two paragraphs inside it, and an image. If you are building this in 2010, it will be a simple HTML page. This page is one big string of markup. You parse it, you render it, done. But Notion doesn't do it this way. For everything that you see on the screen, be it the heading or the paragraph, everything is a block. And all of these things are a separate row in the database. Each row has a type, some content, a parent, and a position among its siblings. That's it. That's the whole abstraction. So this is what a block looks like in the database. So two things to notice here. First, the parent ID points to another block, not a page. Different pages in the documents are also just blocks. The whole thing is recursive. A page contains blocks. A toggle is a block that contains blocks. A column is a block that contains blocks. A page inside a page is a block that contains other blocks. Second, the content field is JSON B. Different block types have different content in them. A heading needs a text, an image needs a URL, a database blocks need some schema and a query. JSON B lets each type capture whatever it needs without polluting the schema. One small note before we move on, real Notion actually stores both an upward parent pointer and the downward content pointers. An array of child IDs on each block for reasons related to the permission system. I'll link their engineering blog post about this at the end of the video. For our build today, we'll keep it simpler with just parent ID, which is the standard recursive tree approach and works fine at the scale we care about. The second decision, model everything as a typed, parented, ordered block, is what makes the Notion's UI possible. Drag a paragraph into a toggle, update one row's parent ID, convert a paragraph to a heading, update one row's type, turn a page into a subpage of another page, update one row's parent ID. Every UI operation maps to a single simple database mutation. Now the hard part. You have got this beautiful recursive data model, but to render a single page, you need to load the page block. Then all of its children, then all of their children recursively until you hit the leaves. A page with 1000 blocks could be 20 levels deep. If you do this natively, one query per level, a single page load becomes hundreds of rounds of trips to the database. So how do we solve this? There are three ways to solving this. First option. In Postgres, they support recursive common table expressions. You write one query that says, give me this block and all their descendants. The database walks the tree internally and returns a flat list. You reconstruct this tree in memory, one round trip, no matter how deep the page is. This is what most people end up doing. The second option, materialize path. Instead of just storing the parent ID, you store the full path from the root. To load a page, you query for all the blocks whose path starts with this page ID. The reads are fast, but now every move operation has to update the paths of every descendant, so it is expensive on the writes. Option 3, nested set model. Each block has a left and right integer. All the descendants have left and right values between their parents. Reads are fast, inserts and moves require renumbering, which gets very painful at scale. So for a Notion style app, the recursive approach, which was the first option which we discussed, is the right call. Pages are read way more often than they are restructured. The tree depth is usually shallow. Most pages are just 3 to 5 levels, not 20. And Postgres handles recursive CTEs efficiently with the right indexes. So that's the read path. We are going with this. Now talking about the write path. The interesting problem here is ordering. So since everything is a block, and if your block have a position field that is just an integer, then every time someone drags a block into the middle of the list, you have to renumber every block below it. That's fine for a 5 block page, but it is a huge problem when someone drags a block in a 1000 block document, or when 10 people are doing simultaneously this reordering and their renumberings conflict. The solution Notion uses, and what every modern doc style app uses, is a fractional indexing. Instead of integer positions, you see strings or fractions that can be inserted between two values without renumbering. For example, let's say the block A is A0, block B is A1, and block C is A2. And now you reorder block B and C. So now the new position for block C will become A1V, which is alphabetically between A1 and A2. No renumbering, no conflicts. Infinite insertions are possible at this granularity. There are many libraries which can handle this, and you don't have to write anything from the scratch. That's the right path. Single block updates, no cascading renumbers, conflict tolerance. Now I want to cover what we are not building today. So I'm going to upfront about the scope. A real Notion has too many big pieces, and I'm not building all of that in this video. The first is real-time collaboration. When two people edit the same block at the same time, you need a conflict-free replicated data type. Generally, CRDTs are used or operational transforms are used. And this topic deserves its own video, or maybe even 3 videos, because it's extremely complex. We are skipping it today, single user editing only. If you want me to cover CRDTs as a follow-up, let me know in the comments. The second is permission inheritance. In real Notion, a page inherits across from its parents unless it is explicitly overridden. To check whether you can see a block or not, the system has to walk until the tree finds an explicit condition that you cannot access this page. There are caching tricks to make this fast, but the architecture is not that simple, and we are going to ship with simple per page permissions today. So it is as simple as you own a page or you don't. So what we are building is the full block model that we discussed, the recursive page tree with proper rendering, fractional index ordering, basic auth, and AI block that use an LLM to summarize a page. And this will be end-to-end deployed and work. So talking about the stack, so we need Postgres for the block model and the recursive CTEs. We need auth so that users can have private pages. We need a model gateway for the AI summarize block. And I need to deploy it somewhere with a real URL because a Notion clone on a local host is not interesting. I'm using INSForge for the backend, and they're sponsoring this video also. The honest reason I picked them beyond the bundling is the way they integrate with the AI coding agents. Let me show you, because this is the part that actually changes how you build. So I'm going to drive this entire backend through Claude Code. To do that, I connect Claude Code to the INSForge MCP, which gives the agent direct access to my live backend. The schema, the auth config, model gateway, edge functions, everything. So I just run this one command with the API key which I can get from INSForge. The same pattern works for all the editors which you might be using. It can be Cursor, Codex, Anti-Gravity, anything which can access MCPs, they can access INSForge. The agent gets a set of tools that talk to your backend. Now the interesting part. The first thing Claude Code does when I start the session before I write any code is call INSForge metadata. That returns a structured snapshot of the project, what tables exist, what auth providers are configured, what storage buckets are set up, what AI models are available, what real-time channels are open. The agent has full context of the backend state before even generating a single line of. Now this is the difference between the AI generates code that hopefully works, and in this case the AI knows exactly what the backend looks like, and it will automatically write code that fits it. Now let me describe to Claude Code what I want. I put this prompt. It is running INSForge DB migrate. It will enable the RLS, which is row level security. It's writing the policies. Now migration is applied. Schema is live. That took maybe 90 seconds. Without the MCP, this would have been writing the SQL by hand, running migrations through some other tool, configuring auth, and all of it is just with just INSForge MCP and Claude Code. Now talking about the recursive CTE. The schema is in place. The read path, which is the recursive part which is required for loading a page. I'm going to let Claude Code take a first pass because this is exactly the kind of thing where agent can see the live schema through the MCP, and it can write the exact code which will be required for accessing this state. It already knows the column names, the types from the metadata, and I don't have to explain anything. So I just paste in this prompt and it generates this query. So this simple query, that's the only thing which returns the entire page as a flat list, and the front end can reconstruct this tree from just the parent ID. There's the page, all the blocks in order in one round. The index we set up in the schema is what makes this fast. Without it, the recursive join has to scan the whole table at every level. This is the read path working. Now the AI block which we talked about to summarize the page. So when you create this block, it takes the content of the page above it and returns a summary. So I'm putting this on the backend as an INSForge edge function. It runs as a serverless runtime. It has direct access to the database, and the model gateway is already configured using INSForge again. Cloud Code can deploy it through the same MCP connection. We don't have to go anywhere else. So I just give it this prompt, and you can see that Cloud Code is calling INSForge to create the required edge functions. It's generating the code, and it will also deploy it. The agent already knew the schema from earlier. It also knew which AI models were available through the gateway because that came back in the metadata call. So it picked an appropriate model without me having to specify, and it also wrote the entire function and deployed it through the MCP connection. No separate model API key required, no environmental variable config required. This makes your work extremely fast, and I really like this about INSForge. So the backend is deployed already. For the front end also, I gave Cloud Code to build a Next.js app, and we just need one more prompt to deploy it. That's it. And I paste this prompt and done. Now we can go to the given link and see how our Notion is working, which we built in just 15 minutes. So as you can see, it already added the authentication both with email and Google. I logged in with Google. Now I can create a new page. So let's say I create a page and give it a heading, what is MongoDB. I can choose between different types of constructs, heading 1, heading 2, bullet list. I choose a quote here, and I'll put just one of the quotes. But as you can see that each of these will create a new database entry in the database. So I can, if I choose a heading 1 and put some content under it, all of it should be linked to the heading 1 because this block is a part of the above block, and all of these things should be connected to the page which we created. So I can add different types, heading 1, heading 2. Now I will use summarize block to see if AI model is connected or not. That we get the AI summary for the page that we have, it all automatically puts it into a block. Now we go to the database and see what are the entries created. So as you can see, in each of them there is a owner ID field which tells me that I am the owner of that page, and only I can access those documents, no one else can. Similarly, there is a parent field which tells that this is the parent for a field. So we have a working block model, working page tree, fractional ordering, working AI block backed by edge function, real database, real auth, real model gateway. Everything is real, and the total time from the empty folder to deployed app is very low. Half of that was me reading what the agent wrote and pushing back on it. So this was how the Notion data block looks like, and how would you build Notion clone if you had to start. Now this is again just a start. As I talked about, there are much more features which Notion offers, like collaborative editing, which are not that trivial and hard to implement, and I'll cover them definitely in some other video. If you like the video, then definitely comment and like it. I'll put everything, this complete workflow and also link to INSForge in the description. You definitely go and check it out.